Okay, in the previous lecture, you have learned the division by t property, which says that if Laplace transform for ft equal to fs, then Laplace transform for ft over t. So divide by t. So division by t property, which is equal to the integral of fs ds from s to positive infinity, provided the limit for ft over t when t approaches 0 exists. Now we are going to learn the Laplace transform of derivative. Okay. If the Laplace transform for yt is equal to ys, by definition of Laplace transform, the Laplace transform for yt is equal to the integral of exponent negative st yt dt from 0 to positive infinity. Then, the Laplace transform for first derivative of y prime t by using the definition of Laplace transform will be equal to the integral of exponent negative st in, if this is yt, this is yt. If now you want to find the Laplace transform of first derivative, you just replace the yt here by y prime t. And to solve this integral, you can use the integral by part, where you have the integral of u dv, where the u is exponent negative st, your dv is actually y prime t, y prime t here, dt. Then the result is uv minus integral of v du. Okay, from the u, the u prime is u prime of, this is the du. The integrates, you differentiate u respect to, this is respect to t. Differentiate respect to t. So we have negative, when you differentiate respect to t, s is a parameter or constant. That's why you have a negative s exponent negative st dt. dv is y prime t dt. To find the v, you integrate your y prime t dt, you get yt. Hence the integral u dv, or the integral of exponent negative st y prime t dt, will be equal to u times v minus integral of v du. V du. That's why the result you will have here u times v. So exponent negative st multiply yt. Since we integrate it from 0 to infinity, so you have to put in the limit 0 to infinity minus v du. So minus with negative become plus as integral of exponent negative st yt dt from 0 to positive infinity. Then when we plug in the upper limit of infinity, remember that in the first lecture, we have told you that exponent negative s infinity will be approaches 0, and the substitution of upper limit will yield to 0. Then minus with substitution of lower limit. So exponent 0 is equal to 1. Hence you have minus y0 here. Remember, by definition of Laplace transform, the integral of exponent negative st yt dt from 0 to infinity is actually is the Laplace transform for yt. You will get ys. So hence you will get this is sys. So that's why you will get Laplace transform. Laplace transform for first derivative, the result is sys minus y0. You have the formula here. in the table of the Laplace transform. If your ft is yt, your fs will be ys. Okay, if you have your ft is y prime t, your fs here will be s ys minus y0. And we are going to show you how we get the Laplace transform for second derivative. We'll use this result in order to solve the first order and second order differential equation by using Laplace transform. Okay, now if you want to find the Laplace transform for second derivative, the same thing using the Laplace transform for y double prime t by using the definition of Laplace transform. You replace the yt here by y double prime t. Again, use integral by part. Same thing, we choose u as exponent, negative st. dv is the y double prime t. This one you have dt. So u prime will be with differentiate respect to t, where the negative s is a constant or parameter. That's why you get negative s exponent negative st dt. From dv, we integrate respect to t. That's why we'll get y prime t. Hence, the result we will have uv, mean the Laplace transform for y double prime t, we'll get exponent negative st multiplied with y mean Laplace transform for y double prime t. This is using definitions of Laplace transform. And to solve this integral, we use integral by part, where the result is uv, which is exponent negative st y prime t. Since the limit of integral is from 0 to infinity. And remember, minus integral of v du. U prime here is the du. So minus with negative, so become plus s integral of exponent negative st y prime t dt. Again, solving this, plug in the upper limit exponent negative st, you'll get this upper limit substitution equal to 0 minus substitution of the lower limit into variable t, because we integrate respect to t. So exponent negative s0 is actually exponent 0, which is equal to 1. Here you have minus y prime 0, which this is here. And then plus, this is integral of v du. So integral of exponent negative st y prime t dt is actually the Laplace transform, right? This is actually the Laplace transform for y prime t. Y prime t. Where you obtain just now, Laplace transform for first derivative of y prime t is actually here the s, so s here is s ys minus y0. Hence the s you expand in the bracket become s squared ys. So s multiply negative y0, you have negative s y0 minus y prime 0. Hence look back, this is a table of Laplace transform. Laplace transform for yt is ys. Laplace transform for y prime t will be s ys minus y0. Laplace transform for second derivative y double prime t is equal to s squared ys minus s y0 minus y prime 0. Which is here. Laplace transform, for second derivative, you get s squared ys minus sy0 minus y prime 0. Laplace transform for first derivative. sys minus y0. So we can use the first derivative, second derivative here to solve the first order and second order differential equation later on. And then to show the applications of Laplace transform of derivative, let's look at two examples here. Example 1, let's ft is sin t. Find the Laplace transform of y prime t. You know that y prime t actually you have, you differentiate sin t is actually you have cos t. Cos t. In the first lecture, we have shown the Laplace transform for cos t using definition of Laplace transform, and we get the result is actually Laplace transform for cos at is actually s over s squared plus a squared, and we are going to use Laplace transform of derivative to show that if we differentiate sin t, we get cos t, and the answer is actually s over s squared plus a squared. And then you have here on the first derivative. So Laplace transform for y prime t is sys minus y0. So if Laplace transform for f, then you just change the y here to f. So this is capital F. The result of Laplace transform, we use a capital symbol. So this is mean Laplace transform for f prime t will equal to s fs minus your f0. Which is on the next page. So Laplace transform for f prime t, from y you change it to f, y change to f, y you change to f. Given the ft is sin t, when t 0, so sin 0 equal to 0. So Laplace transform for f prime t, s fs. To find the fs means you do the Laplace transform for sin t, which is equal to 1 over s squared plus 1. So you get s by s. Then you plug in fs multiply with s. That's why you get the result for Laplace transform for f prime t, and because f0 is 0, that's why you get the result is actually s over s squared plus 1. Which is tally back with what you have done in the first lecture. We have shown that the cos if 1t will be s over s squared plus a squared. And here is actually given the ft is sin t, as you know, if you differentiate sin, you will get cos. Means your f prime t is actually, as you know, f prime t is actually cos t. Then you use the table of Laplace transform. Cos t will be, the Laplace transform will be s over s squared plus 1. Here we purposely want to apply the first derivative of Laplace transform. Mean to get cos t, you can find first derivative of sin t. Mean Laplace transform for f prime t will be s fs minus f0. Where your ft sin t. So when t 0, sin 0, we have 0. So this term here is 0. Then you need to find the fs. Fs is Laplace transform for your sin t, which is 1 over s squared plus 1. And then Laplace transform for f prime t is actually s multiply your fs. So you get s over s squared plus 1. Hence, we have proved that actually the Laplace transform for first derivative we can use is this formula. So Laplace transform for sin t you get here, which is tally with the Laplace transform for cos t. The last example, find the Laplace transform for ft equal to t squared using the transform of derivative. Okay, you want to find ft equal to t squared. Okay, of course, okay, using the, you know that if we use a Laplace transform for t squared using table of Laplace transform. Okay, or in the first lecture, we have already shown, okay, how you get the formula for t power n using definition of Laplace transform, where the Laplace transform for t power n is actually equal to n factorial over s to the power n plus 1. Hence, Laplace transform for t squared will be 2 factorial over s to the power of 3. In the result for Laplace transform of this one, Laplace transform for t squared is actually by using the table of Laplace transform in the first lectures. You know the answer should be 2 factorial, which is equal to 2 over s cubed. But here we would like to get Laplace transform for t squared using Laplace transform of derivative. So how you get t squared is actually, if you ddt, this is like 4. If you ddt 1/3 t cubed, so 3 times 1/3 we have 1, so t squared. If you ddt 1/3 t cubed, you will get back t squared. So in order to get the Laplace transform for t squared now, we are going to use Laplace transform of first derivative. Means Laplace transform for f prime t is actually s fs minus f0, where your ft is actually here. This is the ft. Alright. Your ft is 1/3 t cubed, then you can get your f prime t is actually t squared. So that's why Laplace transform for your f prime t, where the f prime t is actually your ft is 1/3 t cubed, then f prime t is t squared. The result is s fs minus f0. So to find the fs, this one, you have to do the Laplace transform for 1/3 t cubed. Against 1/3 t cubed, we use this is actually from table of Laplace transform. So you have 1/3. Laplace transform for t cubed is actually 3 factorial. Divide by s to the power of 4. 3 factorial is actually 3 times 2 times 1. That's why 3 and 1/3 cancel. You get 2 over s to the power of 4. So the Laplace transform for f prime t is your s fs. Laplace transform for t squared is actually equal to Laplace transform for ddt your ddt 1/3 3 cubed, you will get t squared. And then this is Laplace transform for first derivative will be equal to s fs. S fs, to get fs you have to find the ft is actually 1/3 t cubed, and then s multiply fs. So will be, this is the fs multiplied with s, so you have 2s over s to the power of 4, and you get 2 over s cubed. It's actually faster. Laplace transform of t squared, you use table of Laplace transform, straight away you have 2 factorial over s to the power of 3. But here we just want to show you the application of first derivative. Later on, we use the Laplace transform for derivative to solve the, actually, we are going to use this one, mean Laplace transform for first derivative to solve the ODE. Laplace transform for yt is ys. Laplace transform for y prime t is s ys minus y0. Laplace transform for second derivative s squared ys minus s y0 minus y prime 0. And here we purposely want to show that actually Laplace transform for t squared is actually equal to Laplace transform for first derivative of 1/3 t cubed. 1/3 t cubed, you get t squared. So this is you have the derivative form. Laplace transform of derivative first derivative, you have s fs minus f0. Okay. To get the fs, you have to identify your ft. Ft is here. 1/3 t cubed. 1/3 t cubed. Hence, okay, from ft you find fs, which is Laplace transform of ft. So because to find the Laplace transform for t cubed, we use the table of Laplace transform. There will be 3 factorial over s to the power of 4. Simplify, you have 2 over s4. And then, okay, here, Laplace transform for first derivative, s times fs. So 2s over s4, you get 2 over s cubed. Okay, with this, thank you, okay, for attention and watching, okay, this Laplace transform of derivative video.